Number 10. The ALH 84001 Martian meteorite. In the freezing, desolate expanse of the Allan Hills in Antarctica, a team of researchers in 1984 stumbled upon a dark, greenish-brown rock resting on the ice. After chemical analysis, scientists realized this wasn't just any space rock. It was classified as an SNC meteorite, meaning its origin was unmistakable. It came from the surface of Mars. Around 15 million years ago, a massive asteroid impact on the Martian surface blasted this chunk of rock into space. It wandered the cold void of the solar system for eons before finally being caught by Earth's gravity and crashing into the Antarctic ice roughly 13,000 years ago. But the true bombshell dropped in 1996. A NASA research team sliced the meteorite open and examined its interior using highly advanced electron microscopes. They didn't find little green men, but they found something that fundamentally shook the scientific community. Nested within the rock's ancient fractures were tiny, segmented, worm-like structures clustered together in tight colonies. At a nanometer scale, these formations looked virtually identical to fossilized nanobacteria found right here on Earth. Alongside these tantalizing physical structures, the meteorite contained a cocktail of chemical signatures that are generally considered the hallmarks of biology. The rock was laced with polycyclic aromatic hydrocarbons and complex carbonate globules. Most shockingly, it contained tiny, perfectly formed crystals of magnetite. These microscopic magnetic crystals were chemically and structurally indistinguishable from the exact kind produced by magnetotactic bacteria on Earth, which synthesized them biologically to navigate along magnetic fields. The announcement sparked a fierce, decades-long scientific debate. Skeptics argued that while the structures looked biological, intense heat and shock from the asteroid impact that launched the rock could theoretically forge the magnetite and hydrocarbons through purely abiotic geological processes. The fossils themselves might just be unusual mineral formations or artifacts created during the electron microscopy preparation. Whether ALH 84001 contains actual Martian life remains heavily contested today. However, its impact on space exploration was absolute. It essentially birthed the modern scientific field of astrobiology, forcing scientists to rigorously define what constitutes a microscopic biosignature and directly driving the creation of NASA's Mars rover programs. It proved that to find alien life, we must look at the microscopic building blocks of worlds. Number 9. Titan's vinyl cyanide. When we search for life in the universe, we often suffer from what astrobiologists call water chauvinism. We assume that biology requires liquid water because absolutely all life on Earth depends on it. But Saturn's largest moon, Titan, forces us to violently expand our imagination. Titan is the only moon in our solar system with a thick, dense atmosphere, dominated by nitrogen and organic haze. Even more incredibly, its surface is covered in vast lakes, winding rivers, and rolling seas. But these bodies aren't filled with water. They are filled with liquid methane and ethane, existing at a mind-numbing minus 179 degrees Celsius. In liquid water, terrestrial life relies on lipid bilayer membranes to form the outer boundaries of cells. These membranes are the crucial walls that keep the chaotic outside environment separate from the highly organized chemical machinery operating inside the cell. But if you were to drop an Earth-based lipid membrane into liquid methane, it would immediately become rigid, freeze, and shatter. Water-based biology simply cannot function in Titan's hydrocarbon seas. Enter a remarkable molecule called vinyl cyanide, also known in chemistry as acrylonitrile. In 2017, researchers analyzing archival data from the Cassini spacecraft and the Atacama Large Millimeter Array confirmed that massive quantities of vinyl cyanide exist in Titan's upper atmosphere. The molecule is constantly forming in the haze and raining down by the ton into the methane lakes below. Why does this matter? Detailed chemical simulations by researchers at Cornell University demonstrated that in a bath of liquid methane, vinyl cyanide molecules could spontaneously link together to form flexible, microscopic, hollow spheres. The researchers dubbed these theoretical structures azotosomes. These spheres would function exactly like cell membranes on Earth, remaining stable, porous, and flexible even in the extreme, freezing cold of Titan's liquid natural gas oceans. The discovery of vinyl cyanide raining onto Titan doesn't outright prove there are alien microbes swimming in its lakes, but it proves that the environment possesses the exact chemical ingredients necessary to construct the fundamental architecture of life, entirely independent of water. It suggests that biology might be a universal constant that simply adapts to whatever solvent happens to be raining from the alien sky. Number 8. Europa's ocean carbon. Beneath the heavily cracked, radiation-scorched ice shell of Jupiter's moon Europa lies a dark, global ocean of liquid water. This hidden sea is kept warm by the immense tidal friction generated by Jupiter's massive gravity, which constantly stretches and squeezes the moon's rocky core as it orbits. We have known about this subsurface water for decades, making Europa one of the absolute premier targets in the search for extraterrestrial life. But water alone isn't enough to spark biology. Life requires a constant energy source, and crucially, it requires the right chemical building blocks, primarily carbon. For years, scientists agonized over whether Europa's hidden ocean was just a barren, sterile body of pure water, or if it contained the rich organic chemistry necessary to ignite and sustain biology. Because the ice shell is many kilometers thick, it is nearly impossible for our current probes to sample the ocean directly. But Europa's icy surface is dynamic, and sometimes the deep ocean communicates with the surface above. In 2023, astronomers pointed the powerful James Webb Space Telescope at Europa, focusing specifically on a region called Terra Regio. This area is known as chaos terrain, where the moon's ice has been violently broken, tilted, pushed around, and frozen again. There, staring at the chaos terrain, the telescope detected a highly concentrated signature of carbon dioxide. The presence of carbon dioxide on Europa's surface is a massive revelation because the molecule is not stable there. The relentless bombardment of highly charged particles trapped in Jupiter's brutal magnetic field would obliterate surface carbon dioxide over relatively short astronomical timescales. The fact that we see it concentrated purely in a region of recently disrupted ice means it could not have been delivered by meteorite impacts. It must have been deposited there recently, welling up from the dark, warm ocean below. This discovery confirms that Europa's subsurface ocean contains abundant carbon. It implies that the rocky seafloor is actively interacting with the water, potentially hosting hydrothermal vents exactly like those on Earth's deep ocean floor, where many scientists believe terrestrial life originated. Europa isn't just a frozen water park. It is a chemically rich, geologically active environment that possesses the exact ingredients required to support a living ecosystem. Number 7. Perseverance rover's Jezero Organics. Mars is a freezing, irradiated, rusty desert today, but 3.5 billion years ago, it was a dynamic world of blue skies, a thick protective atmosphere, and flowing liquid water. One of the most promising locations preserved from this ancient habitable era is Jezero Crater, a 45-kilometer-wide impact basin that once hosted a massive lake and a winding, branching river delta. Because it was an ancient watery environment, it is exactly where NASA chose to land the Perseverance rover in 2021 to hunt for signs of ancient alien biology. Perseverance is armed with an incredibly sophisticated instrument called SHERLOC, which uses an ultraviolet laser to map the spatial distribution of minerals and organic molecules on the surfaces of Martian rocks. When the rover finally rolled onto the floor of Jezero Crater and fired its lasers at the ancient lakebed, it found an absolute treasure trove of chemical data. The rover detected a diverse array of organic molecules scattered across multiple rock targets. These weren't just simple, isolated carbon traces. They were complex, varied classes of organic compounds found in direct association with aqueous minerals like sulfates. On Earth, sulfates frequently form when mineral-rich water slowly evaporates, and they are notoriously excellent at trapping, entombing, and preserving biological materials for billions of years without degrading them. It is important to understand that the word organic does not strictly mean biological. Organic molecules are simply chemical compounds containing carbon, and they can be created by abiotic geological processes, volcanic activity, or delivered by crashing meteorites. But their widespread, diverse presence in a former lakebed confirms that the Martian environment was historically rich in the exact building blocks required to assemble life. The specific association between these diverse organic molecules and water-formed minerals suggests that if microbial life ever existed in Jezero's ancient lake, the chemical pathways required to preserve its remains were highly active. Perseverance is currently meticulously sealing these exact rock samples into sterile titanium tubes. In the coming decade, a joint mission plans to launch a spacecraft to Mars, retrieve these tubes, and bring them back to Earth, where the full analytical power of terrestrial laboratories will finally determine if these Martian organics are the fossilized remnants of a dead biosphere. Number 6. LHS 1140b's Eyeball Ocean. When the exoplanet LHS 1140b was discovered 48 light-years away in the constellation Cetus, it presented a frustrating puzzle to astronomers. It orbits squarely within the habitable zone of a red dwarf star, but its mass and radius placed it in a confusing gray area. Was it a dense, rocky super-Earth with a thin atmosphere, or was it a gaseous mini-Neptune completely smothered by a crushing, uninhabitable atmosphere of thick hydrogen and helium? In 2024, data from the James Webb Space Telescope pierced the planetary veil and revealed a world straight out of a science fiction novel. The transmission spectra gathered by the telescope strongly ruled out the hydrogen-rich mini-Neptune scenario. Instead, the data pointed to a dense, rocky world surrounded by a heavy, protective atmosphere, likely dominated by nitrogen, very much like Earth's own atmosphere. But because LHS 1140b orbits a dim red dwarf star very closely to stay warm, the gravitational forces are immense, meaning the planet is almost certainly tidally locked. Tidal locking means the planet does not rotate relative to its star. One hemisphere experiences eternal, scorching daylight, while the opposite hemisphere is frozen in a perpetual, pitch-black night. Without an atmosphere to distribute the energy, the day side would boil dry and the night side would freeze solid. But with a thick nitrogen envelope, heat is effectively circulated globally, creating a profound planetary climate dynamic. Climate models based heavily on the telescope's data suggest LHS 1140b could be a spectacular eyeball planet. The dark night side is covered in a global shell of thick glacial ice, but directly under the star, at the substellar point on the permanent day side, the ice melts completely. This creates a massive liquid water ocean that constantly stares unblinking at its host star, resembling a giant blue iris surrounded by the white sclera of a global ice sheet. This staring ocean could be thousands of kilometers wide and maintain highly stable, temperate conditions perfectly suited for life to thrive. The Terminator line, the twilight boundary where the melting ocean meets the frozen dark, would offer diverse, dynamic habitats. Today, LHS 1140b stands as one of the most compelling and rigorously observed candidates for a habitable, liquid water ocean world beyond our solar system. Number 5. The TRAPPIST-1 Resonance. 40 light-years away in the constellation Aquarius lies a planetary system that looks like it was engineered by an obsessive cosmic watchmaker. The TRAPPIST-1 system features an ultra-cool red dwarf star orbited by 7 roughly Earth-sized rocky planets. The entire system is incredibly compact. All 7 orbits fit easily within the distance between our Sun and Mercury. But the true, awe-inspiring marvel of TRAPPIST-1 is its absolute mathematical perfection. The 7 planets are locked in a near-perfect chain of orbital resonance. For every 8 orbits completed by the innermost planet, the second completes exactly 5, the third completes 3, and the fourth completes 2. This complex, rhythmic gravitational dance prevents the planets from ever colliding or being violently ejected into deep space. It also tells us something vital about the system's history. This delicate arrangement has been exquisitely stable for billions of years without interruption. This deep stability is crucial for the emergence of life. The system is mathematically estimated to be roughly 7.6 billion years old, nearly 3 billion years older than our own solar system. If life requires vast stretches of time to evolve from simple chemistry into complex biology, the TRAPPIST-1 system has offered a significantly longer, highly stable incubation period than Earth ever had. 3 of these 7 worlds, designated planets E, F, and G, orbit squarely within the star's habitable zone, receiving just the right amount of stellar energy to theoretically support standing bodies of liquid water. Because the planets are packed so closely to each other, standing on the surface of TRAPPIST-1e would provide a sky dominated by massive, visible neighboring worlds. They would appear significantly larger than our moon, with their planetary phases and potential atmospheric features clearly distinguishable to the naked eye. Astronomers are currently systematically analyzing these planets using the best telescopes humanity possesses. While early observations showed the innermost planets might be barren rocks stripped of their air by the star's early radiation bursts, the outer habitable zone planets remain the most prime real estate in the galaxy. It is a 7-world system, billions of years older than ours, humming in perpetual gravitational harmony, just waiting to reveal if its ancient shores harbor biology. Number 4. K2-18b's Dimethyl Sulfide Signature. In 2023, the James Webb Space Telescope turned its golden mirrors toward a planet 124 light-years away called K2-18b, and the resulting atmospheric data sent shockwaves through the astrobiology community. K2-18b is a sub-Neptune exoplanet, roughly 8.6 times the mass of Earth, orbiting safely within its host star's habitable zone. Many astronomers suspect it might be a Hycean world, a specific class of planet featuring a thick, hydrogen-rich atmosphere enveloping a deep, global, liquid water ocean. The telescope's spectral analysis confidently confirmed the presence of methane and carbon dioxide in K2-18b's atmosphere. This alone was considered a major scientific victory. A hydrogen-rich atmosphere containing abundant methane and carbon dioxide, combined with a distinct lack of ammonia, is exactly what atmospheric models predict for a warm ocean world. But it was a faint, secondary signal buried deep within the spectral data that truly ignited global imaginations. The telescope detected tentative chemical fingerprints of a highly complex molecule called dimethyl sulfide, often referred to as DMS. On Earth, DMS is an incredibly specific chemical. It is almost exclusively produced by living organisms, primarily by marine phytoplankton floating in our oceans. In fact, it is the exact molecule responsible for giving the ocean its distinct briny sea smell. In the known catalog of atmospheric chemistry, there is no robust, non-biological geological process that naturally produces DMS in significant quantities. The implication of this finding was staggering. We might literally be observing the metabolic exhaust of alien plankton in a global ocean over 100 light-years away. However, the scientific method demands rigorous skepticism. In the months following the initial announcement, independent teams reanalyzed the same data and suggested that the signal might be a false positive, potentially caused by the overlapping signatures of other abiotic hydrocarbons, or simply random red noise in the instrument's detectors. The fierce debate over K2-18b's dimethyl sulfide signature is still ongoing, and future observations requiring much longer exposure times will eventually settle the matter definitively. But the mere fact that we have reached a technological era where we can seriously debate the detection of phytoplankton gas in the atmosphere of an alien world proves we are closer than ever to answering the ultimate cosmic question. Number 3. Enceladus's missing phosphorus. Saturn's tiny, brilliant white moon, Enceladus, is undeniably one of the most geologically active and fascinating objects in our entire solar system. We know with absolute certainty that it harbors a global, liquid, subsurface ocean because the moon literally sprays it into outer space. Massive geysers located at the moon's south pole erupt from deep, parallel fissures known as tiger stripes, blasting water vapor, microscopic ice particles, and complex organic molecules hundreds of kilometers into the dark void. When the Cassini spacecraft deliberately flew through these towering plumes, its specialized instruments tasted the alien ocean. It detected liquid water, carbon dioxide, methane, ammonia, and heavy, complex organic macromolecules. It even found evidence of active hydrothermal vents operating on the dark seafloor. But for years, astrobiologists worried intensely about a missing chemical puzzle piece. Life on Earth requires 6 essential elements to exist: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Phosphorus is by far the rarest of these, yet it is absolutely critical for biology. It forms the structural backbone of DNA and RNA, and it is the core component of ATP, the universal energy-carrying molecule powering all biological cells. Without phosphorus, the vast organic soup of Enceladus would remain hopelessly sterile. For a long time, geochemical models suggested the element might be locked deep within the moon's rocky core, chemically inaccessible to the water above. But in 2023, a dedicated team of scientists proved those pessimistic models completely wrong. They meticulously combed through years of archived data from Cassini's Cosmic Dust Analyzer, specifically looking at individual ice grains that had been ejected from Enceladus and trapped in Saturn's massive E-ring. Inside those microscopic grains of frozen ocean spray, they found clear, unmistakable chemical signatures of sodium phosphates. Not only was phosphorus definitively present, but it was dissolved in the liquid water at concentrations at least 100 times higher than in Earth's oceans. The high alkalinity of Enceladus's water essentially dissolves the rocky core, drawing the phosphates up into the ocean where they are readily available for biology to use. Enceladus doesn't just have a warm ocean, it has a rich, perfectly balanced chemical broth containing every single elemental ingredient required to build a living cell. Number 2. The BLC-1 Proxima signal. In the relentless search for extraterrestrial intelligence, scientists have spent decades pointing massive dishes at the sky, listening to the cosmic static, waiting for a whisper of technology. In 2019, the Parkes Radio Telescope in Australia picked up a signal that was so compelling, so seemingly artificial, that it triggered internal protocols that hadn't been seriously tested since the famous WOW signal of 1977. It was officially designated BLC-1, which stands for Breakthrough Listen Candidate 1. BLC-1 was detected while the massive telescope was staring directly at Proxima Centauri, a small red dwarf star just over 4 light-years away, making it our absolute closest stellar neighbor. It is known to host at least one roughly Earth-sized planet in its habitable zone. The signal appeared squarely at 982 MHz, a tight, narrow-band frequency completely devoid of any known natural astrophysical emission. Stars, pulsars, and quasars emit chaotic, broadband radio noise. Only highly engineered technology produces tight, narrow-band signals like this. The behavior of the signal was textbook alien transmission. It lasted for several uninterrupted hours. It exhibited a slow, precise drift in frequency, which is exactly what you would expect from the Doppler shift caused by a transmitter sitting on the surface of a rotating, orbiting planet. Most chillingly, it passed the ultimate spatial confirmation test. When the telescope pointed precisely at Proxima Centauri, the signal was loud and clear. When the telescope deliberately panned away to check the background, the signal vanished completely. For over a year, the Breakthrough Listen team subjected BLC-1 to the most rigorous, paranoid scientific scrutiny imaginable. If this was real, it meant our closest stellar neighbor hosted a technological civilization, implying the galaxy was absolutely crowded with intelligence. Ultimately, in late 2021, the team published their agonizing conclusion. BLC-1 was not an alien broadcast. It was an incredibly complex, localized form of human radio frequency interference, likely a broken piece of terrestrial electronics whose signal bounced and intermodulated in a way that perfectly mimicked an interstellar transmission. But BLC-1 remains a massive watershed moment. It proved that our automated detection algorithms work perfectly, serving as the ultimate heart-pounding fire drill for the day the real signal finally arrives. Number 1. Oumuamua's unexplained acceleration. On October 19, 2017, the Pan-STARRS telescope in Hawaii detected an object moving through our solar system. It was on a hyperbolic trajectory, traveling at an astonishing 26 kilometers per second relative to the Sun. This extreme velocity proved it was not bound by our star's gravity. It was an interstellar interloper, the first confirmed object from another star system to ever visit our cosmic neighborhood. They named it Oumuamua, a Hawaiian word meaning a scout or messenger from afar arriving first. Almost immediately, the object began defying all conventional astronomical expectations. Based on how its brightness varied as it tumbled through space, astronomers deduced it was extremely elongated, shaped either like a stretched cigar or a flat pancake, unlike any asteroid or comet humanity had ever observed. But the true, unsettling mystery emerged as Oumuamua began its rapid departure. As it moved away from the Sun, the object exhibited non-gravitational acceleration. It was speeding up in a way that simply could not be explained by the pull of gravity alone. Typically, comets accelerate through outgassing jets of vaporizing ice that provide thrust. As the Sun heats the comet, the erupting gases act like a natural rocket engine. However, Oumuamua showed no coma, no tail, and no spectroscopic evidence of gas emission, even when it passed closest to the Sun's heat. Multiple observatories stared at it, desperately searching for the expected cometary exhaust, and found absolutely nothing. It was accelerating through the dark void of space without any detectable physical mechanism driving it. While many scientists attempted to model complex, exotic natural explanations, like sublimating invisible hydrogen or nitrogen ice, Harvard astronomer Avi Loeb proposed a far more controversial and haunting hypothesis. He suggested Oumuamua might be an artificial light sail pushed by radiation pressure, a piece of defunct technology from a civilization we cannot imagine. Oumuamua has long since vanished into the deep dark, leaving us to forever wonder if we just witnessed a strangely shaped tumbling rock, or the silent, dead probe of a distant, ancient intelligence.